All right. So this is the first day of 4-3. It'll take a couple days. But this is called, a lot of times, called the first derivative test. And what we're really trying to find out is where is this particular function either increasing or decreasing. And so what we're really going to do is we're going to find critical numbers or critical values. Because remember, those are the places that the graph can change direction. And those are the only places that it can change direction. Again, does it have to? No. But it can, and it's the only places it can, and that's why it's so important. Would you agree if I had some graph looking like this right here at this section, that particular graph, as I'm going from left to right, is decreasing, correct? It's getting smaller and smaller. And if you take a look at all these tangent lines, they all have something in common. Their slope happens to be negative. And then these are the places that it can change direction, right? That's when that derivative happens to equal 0, or there's another time when the derivative is undefined, or places where it can change direction. Then over here, if the function's increasing, which again, if we're talking left to right, we can agree that that is. If you look at all those slopes are positive. So the rate of change is either negative, positive, or 0, right? I mean, those are your choices. Okay? And so if we take a look at example 1, it says determine the open intervals on which that particular function is increasing or decreasing. So what we're actually going to do is we're going to find out where is it doing neither of those. That's otherwise known as the critical values. Okay, where does it have a chance of changing direction? And so the first thing to do is let's find that derivative, because that's that generator that's going to tell me what that particular function is doing at that time. And then we can set that equal to 0 or find where it's undefined to find critical values, okay, the places it can change. So the derivative on this one, do we have to do product rule or anything like that? I mean, you could do product rule on that second one, but it'd be kind of silly. Okay, this is pretty much just power rule, right? So the derivative is 3x squared, very good.
6x.
Minus 3x, yeah. Okay. And so we're going to look for where that is either equals 0, which means a horizontal tangent, or where it's undefined. So how about 3x squared minus 3x? Are there places that it will not be defined, or are there x values that are not in its particular domain? Or can I pretty much put in any x value I so choose? Right, because there's no variable in the denominator, right? There's no way of making this undefined, correct? So the whole undefined we don't have to worry about. Okay, but that is something you might want to make a note of. Don't have to worry about undefined. Okay, but we do have to worry about where it might potentially equal 0. And so I'm going to do a little bit of algebra here, if you don't mind. Can you agree what I have written in blue, the 3x squared minus 3x, and what I have written in red, the 3x times quantity, x minus 1, are equivalent?
Yes.
Okay. The reason I would do that is a lot of times factoring helps you out when trying to set something equal to 0. Because now I can set either one equal to 0, correct? So if I can figure out what will make this equal 0, it'll be 0 times whatever this thing is over here, and then it's going to be 0. So 3x equal to 0, what do I get out of there? I get that x is 0, right? In other words, if I put 0 back in here, I'll get 0 as a result, correct? Is there another value? Yes. Or if x is 1, by setting that one equal to 0, correct? And that means if I went back here and put 1 in, would I get 0? And I do. Are there any other values, or do you believe those to be the only two? Those are the only two, exactly. And we don't have to worry about undefined. So x being 0 or x being 1 are the only two x values in which this graph could potentially change direction. Again, it doesn't have to, but it can. So here's what I'm saying. Think of this as left to right. And here's how we're going to do it. We're going to create intervals. If you look back at this original, do you agree that that is continuous everywhere? Right? Because we've seen next to the third graph before, right? A little snake-looking thing, right? So we know that that's continuous. We know all the way from negative infinity all the way to 0, this graph has to do the same thing. Now, why would I choose 0? Because do you agree, if I'm on a number line from left to right, the very first one, will I hit 0 first or will I hit 1 first? I'm going to hit 0 first, correct? This graph has to do the same thing that whole time. It has to either be increasing the whole time or decreasing the whole time, because it can't change, because these aren't in there. Those are the only two places it can. And so then we're going to find out, well, what's it doing that whole time? And then from 0 to 1, and do you understand why I'm using parentheses here instead of brackets? Because actually at 0, it is 0, the slope, right? And actually at 1, the slope is 0. So 0 to 1, it has to be doing the same thing the whole time, either increasing or decreasing. And then we've got one more to take a look at. 1 all the way to infinity, right? It has to do the same thing the whole time. Does it have to do it at the same rate the whole time? No, but it has to either be increasing or decreasing the whole time. Okay? Well, how are we going to decide what it's doing? Well, it might be a parabola. Who knows? Okay? I would agree that the graph of this one right here is a parabola. I agree with you there. So what we're going to do is let's just, if it's going to do the same thing the whole time from negative infinity to 0, why don't we just pick some value that's in that interval and find out what it's doing if it has to do the same thing the whole time? Okay. So let's pick any value you want as long as it's in the interval. -1's good. Sometimes I get a little silly and go kind of negative big, like -10 or something like that, because it's easy to see what's happening. But we could use -1. We could use -10. We could choose -1,000,000 if we felt like it. Okay? But I think we probably wouldn't choose that big, right? So here's what we're going to do. Let's just pick -10. That's our choice. And so what we need to do right now is find out at an x value of -10, is this graph increasing or decreasing? How could I possibly figure that out without going to the graphing calculator and graphing that function? How could we possibly do that with the information that's on the board? Substitute it into, if I put it in the original, it's going to give me a y value. Put it in the derivative, because will that tell me the slope? And a positive slope means it's increasing, correct? A negative slope means that's what we just did here, right? If it has a negative slope, it's decreasing. Positive slope, it's increasing. Well, let's find out. So here's why I choose -10. That means put -10 in there and put -10 in there, correct? -10 squared is a really big positive number, correct? Times 3 makes it even more positive, correct? And then -3 times the -10 over here makes it even more positive. So do you agree that -10 gives me a positive answer? Did you notice that I didn't even care what the actual value was? I just wanted to know if it was positive. So from -infinity to 0, the graph of this function is doing what the whole time? Increasing or decreasing? Has to be. Now what if somebody else out there chose -5? Would they have also gotten that it was increasing? Yeah. What if somebody chose -100? Still increasing. What if somebody chose a half? Is there a potential that at a half it's doing something different? Yeah, because it's not in that interval, is it? But it is possible it's doing the same thing. Now why would I choose a half? Well, that happens to be in this interval, correct? You can choose any value in there you want. Can I choose 0 or 1 though? No, because they're not included. So let's choose a half. And I want to know, is it increasing or decreasing? Right? And so what you have to do is put that half into the derivative, because that's what tells me either increasing or decreasing. So why don't you go ahead and do that right now? Well, one thing that some people do is they automatically assume it's going to be negative, and it doesn't have to be. But in other words, I have to put 1/2 in there and 1/2 in there. Here's where general knowledge of numbers can be very helpful. I have to put 1/2 in here and square it. That makes it smaller, correct? 1/4 times 3, about 3/4, right? Okay, exactly 3/4. But minus 3 times a half. Do you agree, just in number sense, that this will be a negative number? Do I care what the negative number is? No, I just need to know that it's negative. So what if somebody else chose a quarter? Would they have also gotten that it was decreasing? What if they chose 1/10? Yeah, they should have gotten the same thing, because we found the two places it can change direction. That's it. Okay, so we know from 0 to 1 it is decreasing without a doubt. And how about from 1 to 10? You just have to choose something. Again, I like to make it kind of obvious. 10. And so you got to put 10 in these x values again, because I want to find slope. I want to know what's it doing, increasing, decreasing, what's going on. And so I put 10 in here, and what do you think is going to happen? Well, we got 10 squared times 3 minus 30. You see why I choose 10 and choose some values that are out there? This is positive. All right. So now, do we know the open intervals on which it is increasing or decreasing? Yeah, we do. But one thing I've noticed on the AP is they're very picky. They don't just accept this. They just basically say, oh, you just got some numbers and positives and negative signs in there. Okay. So actually go to this interval and say that it is increasing. This interval is decreasing. This interval is increasing. Would they technically know? Have they seen that before? And do they know you kind of know what you're talking about? They do. Okay. But they want you to be very specific and say, I know that's what's happening. Okay? So that's just a start. So now you're wondering, well, how does that help me figure out if it's a relative max or min? And you'll find out in our next example how that helps us with that. Well, in your first derivative test, if you have some interval over here and then you have some interval here and it goes negative to positive, do you agree this is what it means? That your original is decreasing and then all of a sudden it's increasing, correct? So it means you have a relative min, okay? And then here, what if you had an interval and then another interval that was going increasing to decreasing, right? It looks like this, right? Increasing to decreasing. In general, it looks like that. And so in this case, you have a relative max. But what if it stays the same? So you go like this, you go like that. Oh, this one was increasing. Oh, it could have changed direction, but it decided not to, and it stayed positive. Then do you have either one? No, you don't. So here it's increasing. It might change. No, I'm not going to. All right? And let's face it, we've all seen that graph before. All right? And so that's what's called a point of inflection. It's not a relative max or min. It's a point where it flips over. And so, or again, you could have one here, decreasing, decreasing. Oh, I'm doing good, I'm doing good, I'm going to change direction. No, I'm not. Just kidding. Okay? And so that's, again, a point of inflection. Okay? So with that in mind, could we tell what we had here? Yeah, it's increasing to decreasing, which means 0 is a relative. It's increasing to decreasing, 0 is a relative max. Then it's decreasing to increasing, so 1 is a relative min. Okay. So there you go. We didn't have to do that on the first one, but there you go. All right, so this is an interesting one. We're just going to do the problem first, and then we're going to use the graph to figure out if we are right. So now we're going to look for relative extrema. Well, we're going to use the first derivative test, and the first derivative test tells us we got to find increasing, decreasing, all that good stuff. So why don't we start with the derivative? How are we going to do the derivative of this one? Yeah, put the x. So what's this called? What's this rule? Yeah, you put the chain rule. Yeah. So we got a 2/3 x squared minus 4. You got to write down the inside. Here's where most people mess up. Yeah, negative 1/3 is your new power, right? Very easy to forget that. And if you remember that, sometimes it's easy to forget this, which is take the derivative of the inside. So 2x. Are we in agreement with that derivative? It's not really in a clean form at the moment, but it is the derivative. And seeing we're actually going to use it now, we might want to do a little bit of algebra, clean things up. So this particular term has a negative exponent, which means it is unhappy, right? And so that would very much rather be on the bottom, right? And really, degree 1/3 power means the cube root, right? Okay, so I'm going to write it that way. Cube root x squared minus 4, right? And how about this 2 right here? That 2 is in the numerator, correct? And how about this 2x over here? That's also in the numerator. So do you agree 4x is in the numerator if I multiply them? All right. Where does this particular 3 go? It's on the bottom. It's happy down there, right? And so we put it down there, and so we'll put it right here. Are you in agreement? That's a way I could clean up that derivative that we had there. So now we have to find critical values or critical numbers. Those are the places it can change direction, and those are the places that it either equals 0 or is undefined. So why don't we do equals 0 first, because that's probably going to be the easier of the two. If we do equals 0, do you agree we're going to take all of this and multiply it up, correct? Which means all of that goes away. So in other words, we end up with 4x equals 0. So now you're really starting to understand why I tell you not probably to multiply out the denominator and don't mess with it until you have to, right? Just let it, because that's a lot of time what's going to happen. And so we find out that it could change direction at an x value of 0. Now, is that the only place that this has the potential of changing direction? No, we can still look at undefined. Now, a cube root. Cube root actually does not cause a problem, because you can take the cube root of a negative, correct? So we're not really looking for imaginaries here, but all that stuff is still in the denominator, correct? So we really don't want the denominator equal to what number? We really don't want the denominator to equal 0. So really, a lot of times, here's what's nice about this. What you really end up doing is setting the numerator equal to 0 and set the denominator equal to 0. And that's really what you end up doing. So let's go ahead and do that. You might be able to see by looking at it what might make this 0, right? Well, I'm going to divide by 3 if you don't mind. So then I have the cube root of x squared minus 4 equaling 0. Is it all right if, as it sits right now, I actually cube both sides, or will that confuse you? We're good with that? Just cube both sides? Cube that side, cube that side. Net result of all of this is that x squared, whoops, not x to the 4th, x squared minus 4 equals 0. Agreed? Now, I know that a lot of you like to do difference of two squares at this point, but you're kind of wasting your time. When there's no linear term, just add the 4 over and take the square root. Right? Because would difference of two squares still work, though, factoring? Sure. But in other words, x squared does have to equal 4 if you add it over. Square root of this side, square root of that side. X is, very good, positive or negative 2. All right, so far, what have we determined in this problem? I got all this algebra, and I got an x equals 0, and x equals positive and negative 2. Those must be the answers then. No, in fact, that's just getting us near the answer. Those are the 3 places that this graph can potentially change direction. We have to find out if it does. And how are we going to find that out? We'll put what back in the derivative? If I put 0 back in the derivative, I guarantee I'm going to get 0. And if I put positive or negative 2 in, I guarantee I get undefined, because that's what we just found. What did we do in the last problem to find increasing and decreasing? Intervals. Okay? So let's go. And if you look at that one, do you see how the original is actually continuous? There are actually no problems there. Because I'm going to square it, take the third root, we're good. Okay? So we're going to go negative infinity. All the way to what? Very good, negative 2. A lot of people want to say 0 at that point. Well done. And then negative 2 to 0. 0 to 2, and 2 to infinity. Is it possible that all 4 of these are positive or all 4 of these are negative? Is that potentially possible? Yeah. And then there's no relative extrema, right? Because they were all positive. They just kept going. A lot of times that's not going to happen, but it can. Don't always assume it's just going to alternate. So now what we need to do is figure out which value, because from negative infinity to negative 2, it's got to do the same thing the whole time. So just pick a value. Doesn't even matter. Just pick something.
Negative 1, 2, 3.
Yeah. Any of the multiple numbers that that person just said, and only one of them is actually in the interval.
Negative 3.
How about negative 10, or just, I like to choose numbers that I can manipulate easily. Negative 3 would be fine. Negative 10 works. Do you agree? Now, here's how I look at this. I got to put negative 10 in here, and I got to put it in there, correct?
Yes.
Do you agree it makes the numerator negative? Right? Makes the numerator negative. What does it do with the, you see how I just do it piece by piece? I'm not trying to get the whole, put negative 10 in, down here. You square it, which makes it positive. Minus 4 is still going to be positive. Take the cube root, it's still positive. Times 3 is still positive. Are we in agreement there? Okay, so this ends up negative over positive. So the net result of that fraction is negative. So we know that it is decreasing this entire time. Can't do anything different. Okay,
Negative 1.
okay, try negative 1. Would you like me to speed things up? Okay. If you put negative 1, and of course I'm going to put that back into the derivative, it makes the numerator negative and denominator negative. Okay, so it's negative over negative, which is a net result of positive. Try 1 probably is a good choice, and this one is positive over negative. Gives me a negative, and then we'll just make somebody happy and we'll choose 3. Whoever that person might be, I don't know. But this one's positive over positive, which is positive. Okay. Again, we sped through that a little bit, but we're just putting it into the derivative to find out if it's increasing or decreasing. So this one here is increasing the whole time, this one decreasing the whole time, and that one must be increasing the whole time. Of course, the only thing that'll throw a monkey wrench in this interval system is if you miss one of the critical numbers. So don't do that. So what this means is my original graph, not the derivative, but my original graph will be decreasing and then increasing, correct? So at an x value of negative 2, what are we looking at? A relative min. So at let's see, relative min at x equals -2. I know that we have a relative max, so I'm going to write that down. So here it is increasing then decreasing on this on these two intervals, right? And it switches at an x value of 0 is where it actually switches. So that's a relative. Nice, right? Increasing to decreasing. Do you agree on this one? It's decreasing to increasing, right? So at x equals 2, it is a relative min. Now, is it very possible that some of those could be absolute max and mins? It is. But does the first derivative test tell me that? No, it does not. They could be absolutes, meaning the biggest overall, but we don't know that for sure. Okay. Of course, with your graphing calculator, is everybody done with that? With your graphing calculator, you get a pretty good idea of what it's doing. But it basically ends up looking like a W. This is not an exact graph, but it basically does something like this. So you agree at -2 and +2, it is a relative. In fact, it's an absolute, but it is at least a relative min and a relative max at x equals 0. Do you agree with the stuff around it, that that's the biggest thing that's there? It is. So the graph does confirm what we found algebraically. Hmm? Oh, I think that's enough for today.